Hello, Honors Geometry students. We will be studying part 5 of your Honors Geometry summer packet, Solving Quadratic Equations. First, you have to know what a quadratic is. A quadratic is simply an equation that has a squared variable in it. So in this case, we have an x squared. Here we have an x squared, and we also have just a plain x, or an x to a power of 1. We'll talk about how to deal with these two different situations in a minute. There are several methods in which you can solve a quadratic, and it really depends on the number of terms that you have. You always want to factor out a greatest common factor before you do anything, because it makes your life easier. After you do your greatest common factor, then you want to focus on your number of terms. If you have two terms, one, and you have just an x squared, or whatever variable it may happen to be, you can solve by rooting. Another option, if you have two terms and you have an x squared and an x to a power of 1. There you will solve by using your greatest common factor. And then we have a special factoring pattern that has two terms. It's known as the difference of two squares. And we'll talk about what that looks like in a second. If you have three terms, you really have basically three options. If your leading coefficient is equal to 1, then is what we call a simple factoring problem, and it should go fairly quickly. When your leading coefficient is not 1, then we will do a process known as Marthing, and we'll talk about what that means shortly. And your third option, if it doesn't factor, you can always use the quadratic formula. So now that I've given you all of your options, let's do examples of each. First, if you notice, we have just a plain x squared. There are no other x's. So all I have to do is isolate. So I will subtract 5 from both sides. So 3x squared equals 15. Then I divide both sides by 3. And here is where the solving by rooting comes into play. Since we have x squared equal to 5, the opposite of squaring is square rooting. So we will root both sides of our equation, and we end up with x equaling the square root of 5. Now, whenever we solve by rooting, we have to include a plus or minus. This is because, technically, if we were working backwards, if we took square root of 5 and multiplied it by the square root of 5, we would get 5. If I took the negative square root of 5 and multiplied it by the negative square root of 5, I would also get 5. So that's why we have plus or minus 5. Now, in this situation, we still only have one x squared, and we could solve this by isolating the x squared. But this follows a special factoring pattern known as the difference of squares. You know you have the difference of squares because you have a difference. They're being subtracted, and you have perfect squares. Nine x squared is a perfect square, and 25 is a perfect square. So you really have two options here. I'll show you the difference of squares factoring pattern. When you're doing the difference of squares, one of your set of parentheses is going to be a plus, and one of your set of parentheses is going to be a subtraction. All you have to do now is basically square root each individual number. The square root of 9x squared is 3x. So that goes in the first position of both parentheses. And then the square root of 25 is 5, so 5 goes here and here. And this is still equal to 0. At this point, all you have to do is set each factored portion equal to 0. So 3x plus 5 equals 0, and 3x minus 5 equals 0. And solve each little equation that you created individually. So x equals negative 5 over 3. Again, we don't want decimals. And add the 5. So x equals negative 5 over 3, and x equals positive 5 over 3. Again, this only works if you have perfect squares, and those perfect squares are being subtracted. Now we have a situation where we have an x squared and an x in the same problem, but we still only have two terms. You might want to make a note to yourself that whenever you have to factor, you always want your equation to be equal. You want it to be equal to 0. Typically, whenever you're working on getting your equation equal to 0, you want to keep your leading term, or your term with the highest power, positive. So I am going to subtract the 5x to this side. In doing so, I have a 0 on the left, and then I have 5x squared minus 5x. Remember, and make a note, you cannot combine the x squared and the x together. They're not like terms. So here, since we only have two terms, and each term has an x, I really need to look at just factoring out a greatest common factor. So looking at which number is a multiple of each. So if you look at their coefficients, they're both divisible by 5. So 5 would be part of the greatest common factor. And since there's an x squared here and an x here, they both have one x in common. So I can factor one of those x's out. Technically, when I factor out a greatest common factor, I'm dividing by the greatest common factor. So if I take 15x squared and divide by 5x, I end up with 3x. And then I still have subtraction, and 5x divided by 5x is 1. It's very common not to show this step, but for example's purposes, I chose to. Now, whenever you're solving by factoring, you just set each portion equal to 0. So 0 equals 5x, and then 0 equals 3x minus 1. When you divide both sides by 5, x equals 0. And we'll add 1. And then divide both sides by 3. So my other answer is x equals 1/3. Again, whenever you're solving a quadratic, typically you're going to have two answers. Now let's get into an actual three-term factoring problem. So looking at the problem, we have an x squared, we have an x. On this other side, we have another x, and then we have a constant term. Again, you want to be equal to 0 to start off with. Since we have an x and an x squared in the same problem, that's just a general rule that we have to follow. So I'm going to subtract the 12x. I will also add this 12. So I end up with x squared, 5 minus 12, is negative 7. And then I have this 12 that I moved over as well, equals 0. Now, when you're looking at a three-term problem, you want to look at your leading coefficient. Since this leading coefficient is 1, all I have to do is think of numbers that multiply to 12 and add up to 7. So numbers that multiply to 12 but add to -7. Sometimes it helps if you make a factor tree, and I'll do that over here off to the side. So numbers that multiply to 12 are 12 and 1, 2 and 6, and 3 and 4. And looking at this, since 12 is positive, I know that both of my numbers have to have the same sign. So they will either both be positive or both be negative. Now looking at this, 12 plus 1 is 13, so that's not 7. 2 plus 6 is 8, so that's not 7. 3 plus 4 is 7. Since I want it to be -7, I'll make it -3 and -4. Once I know the factors, then I can jump to my parentheses. I have x and x here. And just pick your terms. I have -3 and +4. Then each factored portion just gets set equal to 0. So x equals +3 and x equals +4. These are problems that typically a lot of people are able to do in their heads. This one, however, is not as simple. First, this is a 3-term problem. I have to get it equal to 0. So 3x squared plus 4x plus 1 equals 0. There's a lot of different ways to do this and a lot of different methods that you can use. So if you've learned another method in the past, that's fine. Feel free to use it. I like to use a method called MONF. M stands for multiply. So I multiply the 3 and the 1 together. 3 times 1 is 3. Then you think of factors of 3, or numbers that multiply to 3 that add to the middle number, which is 4. This is the adding step, the A. Numbers that multiply to 3 but add up to 4 would just have to be 3 and 1. R stands for rewrite. So what I do is instead of the 4x, I rewrite 4x as 3x plus x. That doesn't change the problem at all. Rewriting it just allows me to do a process of factoring by grouping. The F stands for factor. Notice I just brought down the 3x squared and the 1. So you make 2 groups and you pull out greatest common factors from each group. First group has a greatest common factor of 3x, so you're left with an x plus 1. The second group, it doesn't really have anything in common besides a 1, so you're left with x plus 1. You need this plus 1 here as a placeholder. Your 2 factors are x plus 1. Notice these 2 are the same. If these 2 aren't the same, you've made a mistake. Your other set of parentheses is made up of the pieces you pulled out, so the 3x plus 1. Notice this was equal to 0. So each factored portion gets set equal to 0. X plus 1 equals 0, and 3x plus 1 equals 0. So x equals -1, and x equals -1/3. And that's all I have for you today. Now go ahead and try the problems that are similar to this one in your packet.